Hello and a very warm welcome to GCSE Computer Science at Cranbrook. In this brief presentation, I'm going to talk you through the different topics and the different forms of learning that you will take as you study GCSE Computer Science. Obviously, with GCSE Computer Science, programming is a major feature of it, and you will refine the programming skills you developed in years 7, 8, and 9 to further enhance what you can do with Python and maybe other programming languages such as JavaScript and SQL. You'll learn how to create functions, subroutines, and also work with file handling, which are fairly new concepts to you. And you will create programs that can solve a whole range of real life problems, as well as building interesting little games and simulations for things. You'll learn about what's inside the box in a bit more detail, such as what's inside the CPU, its registers, its control unit, its arithmetic logic unit, and also how these operate and relate with the RAM, which is the primary memory, in order to execute a series of instructions. We'll learn all sorts of information about the CPU, how it can be improved with multiple cores, how its cache memory is really important in terms of its efficiency, and without going into further detail right now, I look forward to explaining these things to you as you do the course. We'll look at how data is stored. So we'll look at solid state technologies such as USB flash drives, optical technologies like DVDs, Blu-rays and CDs, and also standard magnetic storage technologies such as hard disk drives. And with each, we'll learn about how they work physically and also how they are used to store data. We'll learn about how networks function, and this is quite a large topic. We'll learn about how networks, in terms of local area networks, the internet, and also smaller home networks, which are what we call ad hoc, are put together and how they're controlled and how machines on the network can communicate with each other. We learn about switches, we learn about modems, routers, wireless access points, and a whole range of other pieces of hardware. We'll also learn about different configurations such as star and mesh topologies and how these can be different and how they can be budgeted for. As well as learning about networks, we learn about something called attacks. We learn about security, so we can study how active attacks occur, how brute force attacks occur, how hackers get into systems using brute force attacks, how DOSing and DDoSing occurs, which I know a lot of you love talking about. We learn about things such as social engineering, how hackers pretend to be somebody in order to gain the trust of another individual who they then use as their target. We also learn about passive attacks, such as the different types of malware. There isn't just one type of malware, which people often refer to as viruses. There are loads of different types of malware, so we learn about how they work. We also learn about how packet sniffing is used and how people are able to obviously hijack something called DNS, so DNS hijacking. We learn about these passive attacks because they're often a way that hackers can gain access to data without actively having to go out and do the work. They sort of plant a piece of hardware or a piece of software on the network and they basically fill their data bank with all of your private information. So we learn about that. We also learn about active attacks and we learn how to prevent either of those and to safeguard against them. We also learn about operating systems such as Windows, Linux, or Mac, and also Android and iOS. And the one down there to the right, I believe, is Debian. I think it's a new logo for it. We learn about how operating systems work. We learn about tools and features of operating systems, and we learn how to configure them. We also learn about legal and ethical issues. So, for example, is it ethically right to download torrents of films and music? Is it ethically right for us to keep improving and upgrading technology and just throwing away the old parts so they fill huge landfill sites in Asia and in Southwest Africa? Also, we look at advances in science and the science around computer science, such as recently how Elon Musk's company Neuralink has put a chip inside a monkey's brain to now allow it to wirelessly control a computer game. And this has actually been built. So we look at the ethical dimensions. Is it right and why is it right? And is it wrong and why is it wrong? And this usually forms the basis for an 8-mark question that you'll complete within the exam. Moving further on, we've got a second component, which is component 2, and we look at how algorithms work. We build flowcharts for a range of different algorithms to solve a range of different problems. And obviously you can see Sheldon Cooper there from the Big Bang. He built an algorithm to learn how to make friends because Stu the cockatoo, who was new at the zoo, needed an algorithm. That was the belief in the Big Bang Theory anyway. We look at logic gates, and logic gates are part of the central processing unit, and they allow it to be intelligent, and they are little electronic components, I guess, which allow data to flow in certain directions depending on what's been input into them. We learn about binary and hexadecimal, which are ways we represent data. And binary obviously is used by computers to represent our standard denary numbers or decimal numbers. And hexadecimal is an altogether different system, which I'll explain to you in further detail when you take the course. We also learn how sound is stored, how binary ones and zeros are used to encode sound waves, and how we sample at 44,100 times per second in order to get accurate sound waves. And each sample is a binary number representing amplitude. We learn how images are stored, how the individual pixels are coded by binary ones and zeros, and how almost 16,777,216 unique colours can be coded per pixel. We learn about how text is stored in the form of ASCII, which is the American Standard Code for Information Interchange. I know that off the top of my head, you see. And we learn how each letter of the alphabet and also forms of punctuation can be encoded into an 8-bit binary number. Originally it was 7 bits, but we often use 8 bits. And also ASCII's descendant, which is Unicode, which is a lot more than 8 bits and allows us to store letters from a range of different languages around the world. So in a nutshell, we've got component 1, which is systems architecture, memory and storage, computer networks, connections and protocols, security such as the hacking and DDoSing, systems software, and then the legal and ethical and cultural side of things. This is a single paper, which is an hour and 30 minutes, and it's worth 80 marks. Component 2 is more about programming. We learn about algorithms, so how to create flowcharts and represent our programs before we build them. Programming fundamentals, lots and lots and lots of programming. Producing robust programs, so how we make programs maintainable and be suitable for development in the future. Logic gates, Boolean logic, and also programming languages and IDEs, integrated development environments, which are the pieces of software we use to code. And there are loads of different pieces of software we can use to develop Python code. So we'll look at the advantages and disadvantages of those. This is an on-calculator paper, and there are 2 sections. In section B, you'll be tested on your programming skills and how you can construct an algorithm to solve a problem. Not just one problem, but a range of different problems. So obviously that programming development and those programming techniques are really important for passing component 2. So thank you for watching this presentation, and I hope some of these topics really appeal to you and you think, hey, computer science might be the course for me. Until then, I look forward to speaking to you in person and teaching this wonderful course, which I absolutely love teaching.